See then, okay, how we can use this to solve a problem. And what we're going to use to do it is we're going to introduce something called Hamilton's principle. If anyone's ever taken a class in advanced dynamics, is there any mechanical engineers in here? You might have had, yeah. Somebody maybe had a graduate course in dynamics as perhaps a mechanical engineer might have run across this. It's almost always introduced or used in the context of solving dynamical systems. But we can use it in continuum mechanics as well. And it's basically what we're going to use to derive our pore elasticity equations. Okay. Who's ever heard of the colloquial expression in English, the path of least resistance? Right? Yeah. You know the path of least resistance? You know what that means? Right? Typically that's used in like a colloquial way of just, with respect to human action. Like, I'm going to take the path of least resistance. I'm going to do the easiest thing, right? Right? That's what it means. But in mechanics, in physics, everything takes the path of least resistance, right? And it's called, more formally called like the path of least action, or the principle of least action, right? So everything in physics is going to evolve in a way that minimizes the energy, right, required. And so that's what Hamilton's principle is in what I just said in words, we can state in math as where T is the kinetic energy and U is the potential energy. So the total energy is T minus U. And so that's a function, ultimately we're going to plug in values for T and U, and so we'll have a function in the integrand, and we want to know what minimizes that function, so we're going to compute the variation of it, and that's a statement of Hamilton's principle. So in words, you might say that Hamilton's principle would say, among all possible admissible motions of a body, the actual motion of the body is the one that's going to satisfy that equation. Right? Principle of least action. The actual motion of the body is going to be the one that satisfies or minimizes the energy. All right? So let's start with the simplest problem we could imagine, perhaps, and that is a ball of mass m that's falling under gravity. And we can define a little inertial coordinate system over here, and a position vector in the current configuration, if you will, x, right? We'll call this direction x1 and this direction x2. Now, does anyone know, if you have a ball that's falling under the force of gravity, does anyone know what that works out to? Like, what's the equation of motion for that? All right, so let's write F equals to ma. Well, ma, we'll write that first, ma, or in this case, m x2 double dot, right? Because it's going to fall straight down, right? There's no forces acting on it in the x1 direction at all, so it's going to fall straight down. So that's ma equals to the forces. Well, what are the forces? Yeah, minus mg. Right. Huh? No. We're say falling under the absence of air, right? All right. So the equation of motion is then just x2 double dot equal to minus g, right? So we all know that. So there's no point to do Hamilton's principle except just to see how we exercise it to get to that same result, okay? So we'll do that now. And we'll do it for this problem, but then we'll see how useful Hamilton's principle can be when we just add a little bit more complexity. All right. So let's write down the total potential energy. I'm sorry, the total kinetic energy of that guy is going to be 1/2 m v dot v. And the potential energy, U, is going to be mg x2, right? Mg, what?
So why are you taking minus there? Because it's falling in the direction of gravity, right? That's acceleration.
Well, because x2 is positive in this direction.
Oh, okay.
Yeah.
Okay.
Yeah. So it's in the, if you wrote a vector, right, that would be in the negative x2 direction.
Yeah.
Yeah. When you do F equals ma, you have to write in vector form, right? I mean, if I was being really precise, I would have like I, J's, and K's there, right? Yeah. But in this case, it's just one. There's just one direction, so I ignored that part. Okay. When you use Hamilton's principle, another benefit of it, you don't have to. You're starting with scalars, right? You don't have to work in vectors. You're starting with scalars, right? Potential kinetic energy, scalar, potential energy, scalar. All right? Okay. All right. So let's start. I'm gonna compute the variation of the terms one at a time, right? So I'm gonna compute like the variation of t and then the variation of u, right? So we'll start with this. T1, T2, the variation of t dt is equal to, well, we've already, our t is a function of v. We've already figured out what the variation of that is, right? So we're going to T1, T2, partial t, partial v. This was my example when we were computing the variation, dt. Okay. I want to ultimately, I want to deal in position vectors, so not velocity vectors. So what I'm going to do is I'm going to rewrite this partial t, partial v, del, partial v, partial x, partial t, dt. Okay. Remember what I said, that the del operator is commutable with the differential operator? So I can also write this as t1, t2, partial t, partial v, d dt, del x, dt. All right. Now I'm going to use integration by parts. Basically, I'm going to use my integration by parts formulas to move that dt onto that guy. Okay. So when I do that, and maybe next class I'll just review the integration by parts identities for you, but I'll just use it today. We'll review it next time. If you integrate by parts, I get that. Now, this first term, I plug in T1 and T2, right? So it's T2, X is a function of T and X and V, they're all functions of T2 and T1, right? So, or they're functions of T, right? So I put in T2 and T1, which gives me like del X T2 times that minus del X T1, right? Well, there's one thing that I should have been more precise about, is that when we do these, these minimizations are always over definite integrals, right, where we know the boundary values. And so the function at the boundaries is always fixed, right? There is no variation of the function at the boundaries, right? So at T1 and T2, the variation is 0. There is no variation, right? But it's the body is prescribed at those locations, okay? Or the function is prescribed at those locations. So this whole thing basically just becomes 0 because of that. Again, that's because, let me just say, because del x T2 equals del x T1 equals 0. All right. Okay, so then, gosh, I hate it when I do that. Okay, so returning, now we just have the second term, right? Well, we can now go ahead and compute the derivative, partial t, partial v, we're using our definition of t, right? So again, t is 1/2 mv dot v, right? So if we compute this thing, partial t, partial v, we get minus integral t1, t2, d dt mv del x dt, and that is equal to minus t1, t2 ma, right, where a is the time derivative of v, right, the acceleration, del x dt. Okay, so that is the variation of the kinetic energy, then the variation of the potential energy, T1 to T2 of U, del U dt, is equal to T1, T2, mg del x2 dt. Okay, so then writing back down Hamilton's principle, let's include everything. T1, T2, del T minus U dt is equal to T1 to T2. I'm gonna separate now. So we used it. We had a vector x. I'm gonna now evaluate it in terms of the x1, del x1 and del x2. Okay. So I'm gonna write them out. So we had m x1 double dot or ma, right? Del x1 dt plus t1 to t2 m x2 double dot minus mg. I forgot a minus sign right here, right? From there, that minus sign goes there. Also goes there. dt. All right, so all of this is multiplied by del x2 dt. Okay. Now, yeah.
Why are we taking total energy as T minus U? Shouldn't it be T plus U? Like, in case of a pendulum as well, if you consider.
Okay. Maybe I shouldn't have said the total energy, but rather the kinetic minus the potential energy. Yeah. That's what I should have said. The kinetic minus the potential energy.
It's not total
Yeah.
energy.
Yeah, because conservation of energy is like a state. Basically, what you're doing is you're putting a statement of conservation of energy in there, right? Conservation of energy would say T equals U, right?
Yeah.
So move one to the other side of the equation. Right? So this is a statement of energy conserved, right? Right. Okay. So now we got this. We got to this point, and now we're going to use something called the fundamental lemma of the calculus of variations. And I talk about it in the lecture, but basically what that just says is that if you have a function, say g of t times del x dt, then, and if, right, remember we said these variations are arbitrary? What does that mean? What does it mean they're arbitrary? It means they can be anything, right? If they're truly arbitrary, they can be anything, right? So the fundamental lemma of the calculus of variations says that if this is arbitrary and this integral is equal to 0, if this is arbitrary, then what's in the integrand must also equal 0, right? And that's easy to prove because if it can be anything, well, I can let del x equal g of t, right? Then I have the integral t1, t2, g of t squared dt equal to 0. So if then if this is true, that also implies that g of t is equal to 0, right? If you have the integral of something equal to 0, then the integrand of that is equal to 0. So this is a proof of the fundamental lemma of calculus of variations. It basically just says if that's arbitrary, then what is multiplying it is equal to 0. Okay? Now, so then back to this equation, what we're going to do is we're going to invoke the arbitrariness of those functions, right? And we get minus mx1 minus mx1 double dot equal to 0, and mx2 double dot equal to minus mg, or the m's cancel, x2 double dot is equal to minus g. So we got the same, and the first equation is not interesting, right? It's like, there's no motion in the x1 direction. So we worked through all that to get the same answer we could have just wrote down by inspection. Okay? Now let me ask you this question, and I'll leave you to go home and think about it, and we'll work it because we're at the end of class here. What if now I have a ball of mass m falling under the weight of gravity, but that ball is riding on a wire, and the wire has this equation. It's like a wire that has the shape of a parabola. Everybody know the little kid's toy where you have a bead on a wire and you push it around? Right? Okay, so imagine that you have a bead on a wire, frictionless, right? And the shape of the wire is y equals x squared. So now if you try to use Newtonian mechanics to do that, it's going to be really difficult. Because basically you're going to have to, right, what do you do in Newtonian mechanics? First thing you do is you draw a free body diagram, right? So you got to take the bead off the wire and you got to write down the forces, including the reaction force that keeps the bead on the wire. Well, that reaction force is changing as a function of the motion, right? So it becomes really tricky to do that. And that's why I chose this very simple problem to work through Hamilton's principle the first time. What we'll do next time is I'll show you how you can use that same exact machinery to use Hamilton's principle to solve this problem, again, without ever needing to solve for these reaction forces. And then once we see that, we'll go back to continuum mechanics, and we'll use all the kinematics and everything that we've learned to derive conservation of momentum equations for a mixture of a solid and a fluid. And what we'll find out is that the reaction force, the same one that holds the bead on the wire, the reaction force in a continuum mixture of solid and fluid turns out to be the pressure, the pore pressure. The pressure that the fluid imparts on the solid and the solid imparts on the fluid. Right? It's a reaction force. And so And what we'll see in this derivation using Hamilton's principle is that it just falls out. You don't have to introduce it in any way. You don't have to, take the bead off the wire and write down a free body diagram for that. It just works. And so we'll do that next time. All right?